All right, guys, welcome back. In this lecture, we're going to go ahead and finish Chapter 1 on the introduction to the human body. We'll start with a discussion of something called homeostasis. The definition of homeostasis is all body systems working together to maintain a stable internal environment. What this means is keeping everything in the body normal, keeping it all balanced. We don't want any huge fluctuations in the body, whether it's body temperature or fluid balance, like how much water we have in us, or the composition of our blood. For example, how much sodium we have in the blood, or how much calcium we have in the blood. We want all of these different variables to be balanced. We want them to be in a nice, normal range. We don't want big fluctuations. Keeping balance is called homeostasis. And this is a super important concept because this is essentially what the body is doing all the time, right? This is how we stay healthy, is by staying in a nice, normal range. Now, this takes some work, because things around us are always changing, right? Things in the external environment, that's like things outside us, and things in our internal environment, right, or inside us, are changing all the time. So right now I'm in my house and my air conditioner is set to 74 degrees. Outside, it's like 85 degrees. But I can go from inside my house to outside my house, and my body temperature will not change, right? It doesn't matter what the outside temperature is around me. My body temperature is going to remain pretty stable. I'm going to remain homeostatic or in homeostasis. So that's an example of how the external environment changes. The internal environment inside the body changes as well. For example, over the course of this next hour of this lecture, I'm going to drink all this water, right? I'm putting fluid into my body. I'm changing my internal environment, but my body is going to react to that change to stay balanced. So imagine if I drank a gallon of water, I'm adding a ton of fluid to my body. Do you think my body is just going to hold on to that water and just swell up bigger and bigger and bigger? No. What am I going to do? Hopefully you said I'm going to make more pee, right? If I add a bunch of water into my body, well, my body will react to make more urine to get rid of all that extra water because my body wants to stay balanced, right? It wants to stay in homeostasis. Now, if something happens and the body can't remain homeostatic, it can't remain in homeostasis, well, that's when diseases occur. So, like blood pressure, I should have a pretty stable, nice, normal blood pressure. If my body gets messed up for some reason and it can't keep a nice, normal blood pressure, and instead my blood pressure goes up really high, well, now I have a disease, right? Hypertension or high blood pressure. Because I'm no longer homeostatic. I'm no longer in a nice, normal range. So, when we talk about homeostasis, or the way the body reacts to changes to keep balance, we talk about a couple different feedback systems. We'll talk about both positive feedback and negative feedback. The body uses both of these feedback systems, and they're both related to homeostasis in some way. In a minute, we'll see that positive feedback systems actually bring us further away from homeostasis. They're kind of weird. They bring us further away from our normal state. So we don't do this very often, right? These are pretty rare. Negative feedback systems are common. These are most of the systems that we use. These are the feedback systems that bring us to homeostasis. They bring us back to balance. So we'll talk about both of those in a second. But both of these feedback systems, regardless of whether it's positive feedback or negative feedback. Both of these feedback systems or feedback loops have three major components: a receptor, a control center, and an effector. The receptor is something that detects the change in the body. So body temperature, right? If we're talking about body temperature, we have temperature receptors, right? Like sensors all over the body that are constantly monitoring temperature, right? They're scattered throughout our skin, and then we have them in our brain as well. They constantly monitor temperature. If the temperature gets too high, they notice that and they send a signal off to the brain. Okay, so those sensors are receptors. They're the things that detect some sort of a change that's happened in the body. And then again, they're going to send that signal off to the control center, which is the brain very frequently. The control center is the thing that gets the signal and it decides what to do about it, right? So the control center gets the signal, right, that's flashing that says, hey, our temperature is too high. And the control center says, okay, I know how to fix this. And it sends instructions or sends a command out to the body to fix the problem, right? To react to the change. The thing out in the body that it's sending instructions to is called the effector. So the effector is the thing that carries out those instructions, right? That has some sort of an effect in the body. Okay, so there's a change. First, we notice that change with the receptor. Then the receptor tells the control center about it. And the control center decides what we need to do, right? How do we react to this change? How do we fix the problem? The control center sends the instructions out to the body, and the effector is the thing that actually does something. It actually reacts to try and fix the problem. So for example, we've been talking about temperature the whole time, right? We said temperature sensors or receptors sense that the temperature is too hot, and they send a signal up to the brain. And then the brain is our control center. It says, all right, we're too hot. I know how to fix that. Let's sweat. And it sends instructions out to the sweat glands. The sweat glands would be the effector. They make sweat, right? The sweat evaporates, our body cools off, and then we're back to normal. So we're back to homeostasis, back to balance. Now, I told you guys that when we talk about the body reacting to changes, and when we talk about homeostasis, there are two feedback systems involved, or two feedback loops involved: negative feedback and positive feedback. And you guys should be familiar with both of these. You should know the definition of each of these, and you should know an example. So like if I explain some sort of a feedback loop to you, you should be able to look at it and say, that's negative feedback, or that's positive feedback. So in a negative feedback, there's a change in the body, and the body responds by negating that change or that stimulus. So the response of the effector, the response negates the stimulus. Negate is like cancels out. So the body starts to change, right? Something changes in us, and the body reacts by canceling out that change. So it brings the body back into homeostasis. Okay, this is very common because the body wants to be homeostatic, right? The body doesn't want to have huge temperature fluctuations or huge pressure fluctuations. We want to be normal, stable, right, in the middle. So negative feedback is really common. There are tons of examples of this. If our body temperature goes up, well, we start to sweat and we cool back down. We go back to normal. That's negative feedback. The opposite is true. If our temperature goes down, we start to get cold. What happens? We shiver, and that warms us up, right? We go back to normal. That's negative feedback. If I drink a gallon of water, I'm going to make a gallon of pee to get rid of it. negative feedback. Okay. If my blood pressure goes up really high, my body will react to decrease the pressure back to normal. Negative feedback. So anytime the body starts to change and the response is to cancel that change, I'm going to go back to normal, that's negative feedback. Positive feedback is the opposite. In positive feedback, the response of the effector actually increases the change of the stimulus. So there's some sort of stimulus, right? Something in the body starts to change, and the body reacts by changing even more, and then even more, and even more. And it just increases that change. And it actually brings the body further away from homeostasis. Or you could say it brings the body further away from the normal state. Now, this is really rare because the body wants to be normal. There's not very many situations where the body's like, hey, yeah, let's go way off the edge. We normally want to be stable. But there are very rare situations where there's something abnormal happening in the body. And for a short period of time, we'll have a positive feedback loop where we move further and further and further away from our normal state. The two examples that I want you guys to know for positive feedback are blood clotting and contractions during childbirth. I should have a picture coming up soon where we will talk about blood clotting. So right now, let's just talk through the contractions that occur during childbirth. You guys will have to excuse me. I'm like losing my voice already. It's only the third day of the semester. My voice is gone, so that's not a good sign. All right. So contractions during childbirth. The contractions happen in the uterus. So in the female, the wall of the uterus is made of muscle, and it contracts or squeezes to help push the baby out down the birth canal and out of the mom's body. So homeostasis or normal is a relaxed uterus. Thank God. Women would walk around screaming all the time if the uterus was normally contracting. A normal homeostatic uterus is relaxed. However, during labor, right, when a woman is having a baby, the uterus contracts. And if you've ever had a baby or seen a baby being born or watched a movie where a baby is born, you know that the contractions don't start huge, right? They start little. There's one little contraction and the woman's like, man, I think I'm in labor. And then the contraction gets bigger and bigger and bigger and bigger and bigger. That's positive feedback happening. Okay, the first stimulus is just a little contraction, but then that stimulates the release of hormones that cause a bigger contraction. And then that stimulates the release of more hormones that cause an even bigger contraction. And then more hormones cause a bigger contraction. And there's this loop that happens where the contractions are getting bigger and bigger and bigger. That's positive feedback. If it were negative feedback, the uterus would contract and then the body would react to completely stop it and it wouldn't contract again. So you can see that positive feedback is the opposite. This shows us a feedback loop. So let's talk through it and then you guys can decide if this is positive feedback or negative feedback. So over here is where we're going to start. Homeostasis. What's homeostasis? Balance, right? Normal, staying in a nice normal range. Homeostasis in this case is normal body temperature. We'll call that 98.6 degrees, right? Or about 37 degrees Celsius. A stimulus happens, right? Some sort of a change happens. So say this person, was running around, exercising a lot, and they got hot. the body temperature increased. So now the body is not homeostatic anymore. Now it's not normal, right? There's a change. Body temperature went up. So the first thing that happens is the body has to notice this. They need to realize that something has changed. And it does that because of temperature sensors or receptors that are present in the skin and in the brain. The hypothalamus is part of the brain. You don't need to know that. So the temperature sensors sense the temperature, right? And they say, hey, the temperature went up. It's really hot. They send that signal to the control center, which is very frequently the brain. Normally the control center is the brain. And this control center in the brain says, okay, we're hot. I know how to fix this. And it sends commands out into the body, specifically sweat glands to make sweat and release sweat onto the surface of the body. And then also blood vessels dilate or get bigger at the surface to bring the blood to the surface. That way, when the sweat evaporates, it takes the heat away from the blood and actually cools the blood off. So these are the effectors, right? Like the sweat glands that make sweat are the effectors. And then as the sweat evaporates, the body cools down. So here you see the body cools off and normal temperatures restored, and we're brought back to homeostasis. So the body started to change and it reacted to bring us right back to normal, back to where we came from. So is that positive feedback or negative feedback? Hopefully you said negative feedback, right? The body started to change and we canceled that out and went back to normal. That's negative feedback. Looking at this, you see why we call it a feedback loop, right? We start here at normal and we loop around to go back to normal. That's why we call them feedback loops, because they circle around. This is showing us blood clotting. Now, the process of blood clotting is really complicated. If you take anatomy and physiology, you'll end up learning about it in A&P 2, but it's really complex. So I don't care that you know about the actual process, like what's happening. I just want you to understand that whether it's positive feedback or negative feedback. So what is normal for the blood, right? Homeostasis is thin blood, right? The blood should be watery and it should flow really smooth and nicely. It should not be chunky. However, there are certain circumstances where we need the blood to get thick. We need it to clot. That happens when there's a broken blood vessel. So when you get injured or something happens and it tears the blood vessel, all of a sudden the blood can leak out, right? So you see that here in this first picture. The blood vessel broke and now blood can leak out of it. Well, that's a problem. We need to stop the blood from leaking out of that hole. And the way we do that is by forming a blood clot that will patch up that area. So when the blood vessel is broken like this, it releases chemicals. And those chemicals start to activate all of the blood cells that are present. So blood cells get activated and they start to stick to this vessel wall. Well, when these blood cells get activated, they release more chemicals that activate more cells. Then those cells dump more chemicals to activate more cells. They dump more chemicals to activate more cells. And during that loop, when these cells are getting activated, they're getting stickier and stickier and stickier, and they're clumping together, and they form this thick, sticky blood clot. Now that's important, right? It plugs up the broken area so we stop bleeding, we stop losing blood. So that's good. It's necessary in that case. But that's not normal, right? It's not normal for the blood cells to be activated and the blood to be sticky. So while that's happening, that is a positive feedback loop because it's not normal. It's bringing us away from our normal state of thin flowing blood. So it's positive feedback. All right, so we'll change gears a little bit and just kind of mention a few terms that have to do with chemistry. And then in the next chapter, we'll go into chemistry in more detail. The maintenance of life, in order for something to be living, it requires steady metabolism. Now, I think we all use this term metabolism, but not many people know what it actually means, right? You hear people say, oh, I've got a really fast metabolism, or I gain weight easy because I have a low or slow metabolism. And that is kind of accurate. What metabolism actually is it's the sum of all chemical reactions that are occurring in the body. All reactions. There are chemical reactions that are building things up. There are chemical reactions that are breaking things down. All of the reactions that are happening all over the body at once. That's the metabolism. Now, there are two components of metabolism. Metabolism can be broken down, or chemical reactions can be broken down into different types. So the two components or parts of metabolism are anabolism and catabolism. Anabolism includes all of the chemical reactions that are using energy and nutrients to build up more complex molecules. So if you're taking two smaller things and putting them together to make something bigger, that's included in anabolism. So for example, protein synthesis. When we make proteins, we're building something, right? We're making something, we're making something bigger. So that's anabolism. Or you could say those are anabolic reactions. Catabolism includes all of the chemical reactions that are breaking down molecules. So if you have a really big complex protein and you break it down into smaller components, into smaller little amino acids, for example, that's catabolism. So for example, the digestion of food that happens in our GI tract, those are catabolic reactions, or those reactions are included in the body's catabolism. The way that I remember this, our catabolism sounds like catastrophe. And what happens when there's a big catastrophe? Everything gets broken down, right? A hurricane comes through, that's a huge catastrophe. The town gets torn apart and broken down. Catabolism includes the reactions where things are broken down. And then anabolism is building up. Well, anabolism reminds me of anabolic, right? So anabolic steroids, those are the steroids that athletes use to build up their muscles. They're called anabolic because anabolism is building things up. So building up big muscles, for example. Both of these together, so anabolism plus catabolism, that gives us metabolism. So all the reactions together is the metabolism. All right, kind of changing gears again. When we talk about the human body, we use anatomical terminology. And anatomical terminology is a technical language that scientists and researchers and medical personnel all use to talk about the body and diseases, parts of the body. The reason that we use this anatomical terminology is so that people all over the world can communicate with each other using a standard language. Okay, so we use special terms now to talk about different parts of the body or different directions. When we use anatomical terminology, we assume that the body is in a standard position called the anatomical position. So that assumes that the body is erect, right? It's standing up and forward like this. The arms are straight, palms are facing forward, the face is forward, the legs are straight with the toes facing forward. That's the anatomical position. So there's no like flipped around or sideways. You assume that the body is in this erect, straight anatomical position. Now, it can be laying down, right? Think of like a patient in the hospital. They're frequently laying down. So you can be laying down in the anatomical position, either face up or face down. When somebody is laying in the anatomical position, face up, so laying on their back, facing forwards, facing up, that is called supine. When they're laying face down, that's called prone. The way I remember that is supine is the way you're supposed to, right? If you're laying down, it's much more comfortable to lay with your face up than with your face crammed into the bed. So supine's how you're supposed to. That's face up. Prone, you're prone to hurt your nose, right? That's going to cram your nose into the bed. So if you lay prone, you're prone to hurt your nose. Now, included in anatomical terminology are certain anatomical regions. These are just terms that we use to describe broad areas of the body. There are body regions and body parts that we'll see. So body regions like cephalic means the head. Facial means the face. And then on those regions, there are specific parts. So like nasal means the nose. Buccal means the cheek. We'll also look at the abdominopelvic quadrants and the abdominopelvic regions. These are just sections or areas in the abdomen or the abdominal area. Finally, we'll also see anatomical directions. These are special technical directional terms that we use when we're talking about the position of a person or like the location of an injury. We'll use these anatomical directions. So like we don't say above or below or it's right next to it. Instead, we would say, it's lateral to, or it's medial to, it's superior or inferior. We're going to use technical directional terms. When we're using these technical terms, it's important to remember that right and left always refer to the patient's right and left, or the subject's right and left, not yours. So like when I'm looking at somebody, if I'm facing them, it's going to be crisscrossed, right? So it's always their right and left, not mine, and not yours. All right, so here we see different body regions or ways that we can break the body up. The two large regions of the body are the axial region and the appendicular, right? Or the axial portion and appendicular portion. The axial portion of the body is just the part on the vertical axis, right? Axial axis. So if you drew like a straight line through the middle of the body, those are the parts in the axial region or axial portion. So the head, the neck, and the trunk. The appendicular portion refers to the appendages, so the arms and the legs. Specifically, the upper extremities are the arms and the lower extremities are the legs. Each of these portions, right, the axial portion and the appendicular portion, then get divided up into regions. The head and neck, pretty obvious. The upper extremity, we already said those are the arms, and the lower extremities are the legs. And then the trunk, right, is like the torso here, like your chest and your belly. That's divided up into front and back sections. So the anterior trunk is the front of the trunk, so like the chest and the belly. The posterior trunk is the back of the trunk. So like the way that I would use those terms on an exam, like I could ask you the navel, right, which is like the belly button, the umbilicus or the navel is on what body region? Well, the belly button is on the anterior trunk, right? Or I could say, you can see the spine sticking out on what body region? The posterior trunk. Or the elbow is present on what region? The upper extremity. The knee is present on the lower extremity. Then each of these general regions has a large number of specific body parts, right? Obviously, just like you would normally say the head and neck has a nose, eyes, ears, chin, cheek, forehead. Well, we still have all of those parts, but now we give them special technical terms or anatomical terms. And those you see listed here. Now, I'm not going to go through and read all of these to you. I do recommend you kind of glance at them and look through them. You do not have to memorize all of these specific body parts. If you take anatomy and physiology, you will. The very first chapter in lab, you memorize these all. What you guys have to memorize is just the basic stuff, the regions that we saw in the last slide. So you should know head and neck, which is super simple. You should know upper extremity, that's the arm, that the lower extremity is the leg. That anterior trunk means the front of the trunk, so this area. And you should know that posterior trunk means the back of the trunk. So lower extremities, again, the legs. Posterior trunk, right, again, is the back of the trunk. That's super simple. If you plan on going on to anatomy and physiology, I would recommend at least kind of starting to learn these. All right, here you guys see the abdominopelvic quadrants. Abdominopelvic refers to like this area here, the bottom part of the trunk underneath the chest. Abdomen and then pelvis. So the abdomen is like the belly here, and then the pelvis or pelvic is like inside your hips, inside the pelvis or hips. So you put them together and it's abdominopelvic. Now, this abdominopelvic area, we can divide up into different regions. There are 9 abdominopelvic regions, which we'll see in a second, and there are 4 abdominopelvic quadrants, which quad literally means 4. To get these 4 quadrants, you just draw a plus sign that crosses at the umbilicus. The umbilicus is the belly button. The reason we call it the umbilicus is because that's where the umbilical cord attached. So when the fetus is inside the mom's belly, the umbilical cord connects right there at the belly button. When you clip it off, the belly button is what's left. So we call it the umbilicus. So to get these quadrants, you just draw a plus sign that crosses right at that umbilicus. And then we have 4 regions. And you just name them upper and lower and right and left. The only way you could get mixed up is if you don't do right and left correctly. Remember, it's their right and left. The subject's right and left. So in the picture, it's this guy's right and left, not mine. So here's the right upper quadrant and the right lower quadrant, the left upper quadrant and the left lower quadrant. Sometimes we want to be even more specific, and we can divide the abdomen up into regions. There are 9 abdominopelvic regions. To do this, you just draw a tic-tac-toe board on the abdomen and pelvis. The vertical lines go just medial or just inside the nipples. So here and here. And then the horizontal lines, one crosses like just at the bottom of the ribs, and one crosses just above the hips. And that gives you 9 regions. You see the 9 regions listed here. I'm not a huge fan of these. They're almost too specific. So they divide the abdomen up into really small areas, especially on a smaller person, like on a small woman or on a child. These regions are tiny. And if you look over here at the picture, you can see the organs that are underneath. So like the liver, for example, the liver is present in multiple of these regions. So if the liver was, if there's a problem with the liver, the person would have pain in what area? You could say, oh, well, they would have right hypochondriac pain, and they would have epigastric pain, and maybe would they have a little pain down here too? It's just too specific. The organs stretch between multiple areas. Whereas if we were using the quadrants instead, well, the quadrant goes like this. So the liver is almost entirely in this right upper quadrant. So if there was a problem with the liver, I could very specifically say the patient is going to have right upper quadrant pain, right? Or if there was a problem with the appendix down here, I could say that the patient was going to have right lower quadrant pain. But if we use the regions, look, the appendix stretches between multiple regions. So where's the pain going to be? Is it going to be in the pubic region or in the right iliac region? Okay, so these are too specific for me. I prefer the quadrants. And clinically or medically speaking, we frequently will use the quadrants. These are directional terms that we use. Now, instead of going through these right now, I'm going to post a link for you guys. So just underneath this lecture, I'll post a link to a couple more specific videos that I have on YouTube that go through these directional terms. And then I'm also going to post a link to a video on the body cavities they're nice and they're good and specific. So you'll find both of those links just underneath this video on Canvas. So I'm not going to go through these in huge detail on this video. So the planes, a plane is just an imaginary line that goes through the body, or like a 3D axis. Like if you imagine this paper coming through my body, it could come through, horizontally like this, or it could come through vertically like this. So a plane is just a 3-dimensional axis that cuts through the body. Now, we use planes when we do imaging. So like MRIs or CT scans, we'll visualize the body. We'll take like slices of the body parallel to different planes. A transverse plane cuts through the body horizontally like this, dividing it into top and bottom pieces. A sagittal plane cuts through the body vertically like this, dividing it into left and right. And then a frontal plane goes through the body vertically, but it goes this way, separating it into front and back pieces. And then again, a section is just a really thin little slice parallel to that plane. And when we do imaging studies, we'll take a ton of thin sections, like millimeter sections. We'll visualize them over and over and over and over. And then we can put them together and get a 3D image of the body. And we do that when there's some sort of a problem and we're trying to visualize the organs inside. So looking for masses in the lungs, for example. Here you see the planes. Again, the blue one is the sagittal plane, dividing the body into left and right. If it's right in the middle, it's called mid-sagittal. If it's anywhere besides the middle, it's called parasagittal. The frontal plane is this purple one that cuts through the body, dividing it into front and back. And then the transverse plane is this green one, the horizontal one, that cuts the body into top and bottom. I'm going to go ahead and stop there. The rest of these slides, again, are on the body cavities, and I have a really specific in-depth video that I'm going to post for you guys on the body cavities. So I'll update this video right now on Canvas, and then you'll see the 2 links underneath for directional terms and for body cavities. All right, thanks so much, guys. If you have any comments, if you have any questions, go ahead and shoot me an email. Otherwise, I will see you guys tomorrow for tomorrow's lecture.